Okay, welcome back for our third discussion on Chapter 10, the kinetic theory. We have discussed gases and liquids and a little bit about solids. Today we're going to get more specific with regards to solids, and we have a lot of vocabulary to discuss. We're also going to discuss phase diagrams, a fairly important concept in chemistry. So, let's write down some properties of solids, some of which you're familiar with. Number one, solids, of course, have a definite shape. As you recall, liquids and gases, well, take the shape of their container and they occupy the volume of their container. Solids, on the other hand, have a fixed volume and a definite shape. Number two, solids, because the particles are so close together, cannot be compressed. So similar to liquids, in that liquid particles are close together. We can't squish them any closer together than they already are. Number three, solids do not flow like liquids and gas particles. Liquid and gas particles can slide past one another. Solid particles are more locked into position, so they can't slide past one another. So we say they can't flow. And finally, most solids form crystals. There are a couple of exceptions when we discuss amorphous solids, but we will not worry about them in this chapter. Some vocabulary. Sublimation. Sublimation is a change directly from the solid phase to the gas phase without passing through the liquid phase. That sounds interesting. Now your book gives a couple of examples. I'm going to discuss one of them in just a second. My challenge to you is to find a third. So I'm going to give you one, your book talks about another, and I want you to see if you can come up with a third substance that would sublime at room temperature. Now the one I'm going to give you is quite common. Dry ice. Now dry ice is carbon dioxide in its solid form. If I were to take a piece of dry ice and place it on my desktop, that carbon dioxide in its solid form would change directly to carbon dioxide in the vapor form or gaseous form, and you would not see droplets of carbon dioxide condensing or forming on my tabletop. It would go directly from the solid to the vapor or gaseous phase without passing through the liquid phase. Melting point. We'll begin with a quick question. Is water a liquid or solid at 0 degrees Celsius? Now you guys know at 0 degrees Celsius, that's the melting point or freezing point of water. So what's happening to water at 0 degrees Celsius? Is it turning from a liquid to a solid, or is it turning from a solid to a liquid? What's happening there? Well, let me give you the definition for melting point to see if that helps us out a little bit. The definition for melting point is the temperature at which the solid, I'm going to put just an S in parentheses there, and the liquid, so L is of course my symbol for liquid, so the temperature at which the solid and liquid can coexist in equilibrium. Now equilibrium was a concept that we talked about in the last discussion. So at 0 degrees Celsius, what is water doing? Is it turning from the solid to the liquid or the liquid to the solid? The answer is yes. It's doing both at the same rate. Remember equilibrium? The solid is forming a liquid at 0 degrees Celsius. At the same rate, liquid particles are turning back into the solid form. So melting point is the temperature at which the solid and the liquid can coexist in equilibrium. They're turning into each other at the same rate. Okay, next up, liquefaction. The definition pretty much tells you what's happening. You're turning a solid into a liquid, or, in this case, we're going to be turning a gas into a liquid. How can you turn a gas into a liquid? Well, if we add pressure to the gas, we can push the molecules close enough together to where they not only begin to take on liquid properties, but they actually condense and become liquids. Liquefaction, in this case, is the process by which those vapor particles are being pushed close enough together to become a liquid. Now, there's a temperature above which those vapor particles have so much energy, no matter how much pressure we add, we cannot cause them to liquefy. Once we get above that temperature, no matter how much pressure is added, they cannot liquefy. And that's our definition for critical temperature. So it's the temperature above which no amount of pressure can liquefy. Now I'm going to spell liquefy L-I-Q-U-I-F-Y. You can spell it with an E if you want, like I did up here. So the temperature above which no amount of pressure can liquefy a gas. Now interesting, I said above which. Doesn't that imply that at the critical temperature you can liquefy a gas? Of course you can, if you add enough pressure. And that's called my critical pressure. So critical pressure is the pressure that's needed to liquefy a gas at its critical temperature. So I can liquefy a gas at its critical temperature if I add a boatload of pressure. The pressure required to do that is its critical pressure. Now, quick question. Which type of particles have higher attractive forces? Those with high critical temperatures or those with low? Let me give you an example of each. Hydrogen gas is both nonpolar and very, very light in weight. Water molecules are not only polar, they can hydrogen bond. And they have a much larger molecular weight than hydrogen gas. Which particles do you think would have the higher critical temperature? Which particles do you think are harder to pull apart? Or, can I say, easier to stay in the vapor phase? I claim hydrogen gas particles. They have minimal attractive forces, so it doesn't take much energy to keep them as a gas. Water molecules, on the other hand, can hydrogen bond, and they have a bigger molecular weight than hydrogen molecules, so they have greater London dispersion forces. Are easier, they come together easier. They're harder to pull apart, so they have a high critical temperature. So the molecules that have higher attractive forces are those that have a high critical temperature. Okay, our last topic for this discussion is going to be phase diagrams. We're going to look at two different phase diagrams. The first one we're going to look at is for water. So this is the phase diagram for water, H2O. Now I don't have any units or designation for quantity along my y or x axes, so we will have to make some up here as we have this discussion. There's a more detailed representation of this graph in your textbook. So let's come up with a few abbreviations. We'll talk about what these are. T sub n is normal melting point. T sub b is normal boiling point. And then finally, T sub c is our critical temperature. Now, let's go ahead and find out where these are on my graph. First of all, let's talk about the word normal. Normal, when we talk about melting point and boiling point, refers to a specific pressure. It's the pressure on a typical day at sea level, which is 1 atmosphere, or 760 millimeters of mercury, depending upon the unit you're using. Now, like I said, we don't have any numerical values for pressure, so I'm going to say that this point right here on my graph is 1 atm. So, what is the temperature where water melts at 1 atmosphere? Well, isn't melting the equilibrium between the solid and the liquid? See the arrows going both ways, solid to the liquid, liquid to the solid. So let's see. That would be right about here on my graph. And we all know that that's about 0 degrees Celsius for water. What is its normal boiling point? Once again, normal implies that we're at 1 atmosphere. And boiling is when the liquid and the vapor are in equilibrium. So let's see where that is on my graph. If I come across right about here, that would give me my normal boiling point for water, which we know is 100 degrees Celsius. The critical temperature is over here. Notice what my graph does. It starts going straight up and down. That means no matter how much pressure I add, I'm going to be in the vapor phase at a temperature above this. So this is my T sub C, or my critical temperature. Any temperature higher than that, no matter how much pressure I add, no matter how high up I go on the y-axis, I will still be in the vapor phase. Now, triple point. Triple point is the temperature and pressure at which all three phases of a substance, so that would be solid, liquid, and gas, coexist, and our favorite word here, in equilibrium. So the triple point for water would be right here. So we have the solid, liquid, and vapor coexisting at equilibrium. Now, something interesting and quite unique for water's phase diagram is the slope of the solid-liquid line. So line segment AD. Do you notice that it has a negative slope? It slopes to the left. Why is that significant? Well, let's think about this. Let's say I'm at -5 degrees Celsius. What phase is water in normally? Well, let's see. It puts me right about there on my graph at 1 atmosphere. It's a solid phase. What if I add pressure? So we're going to make the pressure rise. And what happens right there? Water begins to liquefy. Even though it's -5 degrees Celsius, we're turning water into a liquid by adding pressure. Think about that. Think about our last discussion in our ice skating example. When pressure is added to water in its solid phase, it wants to go to the lower volume. The lower volume for water is its liquid phase. So we can cause water to liquefy by adding pressure. And its temperature is below its normal freezing point. Quite interesting. So the significance of this line, this shows that the liquid has a smaller volume that means it has a greater density than the solid. That means that the solid will float on the liquid. Water is about the only substance that will do that. There are a few others, but for all intents and purposes, water is the only substance where the liquid has a smaller volume than the solid. That means the liquid is more dense than the solid. You can see that by the negative slope of the line for my solid and liquid on my phase diagram. Now look down here at this temperature and pressure. Water would be a solid. If we raise the temperature at this low pressure, water would actually sublime. It would go directly from the solid to the vapor phase, and it would not pass through the liquid phase. So sublimation would occur below the triple point. Now, in your notes, I made a small mistake. We are not going to look at the phase diagram for hydrogen here. So your notes say hydrogen, please cross that out. And it says to look at page 433 of your textbook. That's no longer valid information. So instead, we're going to look at the phase diagram for carbon dioxide right here. Now, take a look at this phase diagram. Is the slope of the solid-liquid line different for carbon dioxide? Do you notice that it's slightly positive? Remember, water's had a negative slope. CO2 slope has a slight positive slope to it. So what does this tell you about carbon dioxide? Well, let's say I'm at this temperature, and this pressure. If I raise the pressure, I stay in the solid phase, don't I? Remember water? When I raise the temperature, because of the negative slope, didn't I cross over into the liquid phase? For CO2, that does not happen. So what does this tell you about carbon dioxide? Well, instead of the liquid having the smaller volume, the solid has a smaller volume. That means the solid is more dense than the liquid. So, solid carbon dioxide would sink in liquid carbon dioxide. Interesting to note, though, we don't often see liquid carbon dioxide, do we? We normally just see the solid or the vapor. Take a look at the phase diagram to find out why. At 1 atmosphere pressure, CO2 will sublime at negative 78.5 degrees Celsius. That means it goes from a solid to the vapor phase. So what would its normal melting and boiling points be? Good question. Does it have a normal boiling and melting point? Remember, normal means 1 atmosphere. So at 1 atmosphere, does it change from a solid to a liquid or a liquid to a gas? No, it does not. The liquid phase doesn't even exist until we get into pressures above 5 atmospheres. So therefore, does it have a normal boiling and melting point? It has no normal. Remember, normal implies that the pressure is 1 atmosphere, melting point or boiling point. So we can have carbon dioxide in the liquid phase, but the pressure needs to be higher than the triple point pressure, and the temperature needs to be higher than negative 56.4. So if we're at room temperature, which would be somewhere around over here, you will notice that at 1 atmosphere, we will only find carbon dioxide in its gaseous phase. Now we can have some solid carbon dioxide, but as it heats up to room temperature, it sublimes, doesn't it? And we miss the liquid phase completely. So, what pressure is needed to liquefy carbon dioxide at room temperature? Well, let's take a look at our graph here. We're going to say this is about room temperature. This is around 23 degrees Celsius. It actually might be a little bit further to the right. But let's move up here, and we can read our graph. It turns out that it's somewhere around 60 atmospheres. That's 60 times the normal atmospheric pressure. So if we wanted carbon dioxide to exist as a liquid at room temperature, we'd have to add in excess of 60 times the normal atmospheric pressure. So what pressure is needed to liquefy CO2 at room temperature? It's around 60 atmospheres. Quite a bit of pressure. So are we likely to see liquid CO2 at room temperature? No, we are not. We will see the solid or the vapor phase. Alrighty, well that wraps up part 3 of our Kinetic Theory, Chapter 10 lecture. There's just a short lecture after this one. We'll talk about energy and change of state, and we'll do that next. So stay tuned. Thanks for your time.